Hi, my name is Enrique Sanchez and I will present affective processes, stochastic modeling of temporal context for emotion and facial expression recognition, work done along with Mani Kumar, Michel Balstar and Georgios Tsimiropoulos. This paper is on the temporal modeling of emotions and facial expressions. Prior works mainly focus on building stronger backbones, ignoring the temporal dependencies, or apply recurrent models, which fail to model the long-term dependencies or the underlying temporal context. Newer methods explore the use of attention in the feature level, and few, based on transformers, have started exploring the use of temporal attention. However, these methods fail to model contextual dependencies in a probabilistic way, ignoring that similar sequences might have different future paths. In this paper, we propose affective processes, the very first method for the temporal modeling of emotions and facial expressions that models sequences by looking at them as realizations of some underlying stochastic process, which we aim to discover. We build on the neural processes framework and encoder-decoder architecture for exchangeable or permutation invariant stochastic processes. This implies that, rather than modeling the probability of observing, say, a smile after a yawn or a yawn after a smile, as recurrent models do, we just assume that the probability of observing a smile and then a yawn is the same as first observing a yawn and then a smile. Neural processes assume that training sequences are random functions where the output dependencies are governed by some stochastic latent representation, which is computed from a handful set of input features and labels, known as context. To avoid the need of manually given context, we propose the use of a frozen backbone and a context selection method that, from a set of low-dimensional feature representations and task-specific pseudo-labels, can model the underlying distributions efficiently. In particular, our paper is the first application of neural processes to the real-world scenario of emotion recognition, as well as the first method that proposes the use of a frozen backbone for pseudo-labeling and a context selection method within neural processes. Our method sets new state-of-the-art results in 4 different benchmarks. At training, we will select from a sequence a random subset of frames to be the context. For each of the input images in the sequence, we will produce a set of features and noisy estimates using the backbone. The features and task-specific predictions will be forwarded to the neural processes encoder to produce a per-frame latent representation. Then, all the latent representations for the target sequence will be aggregated through the mean operation, producing a global fixed-dimension latent representation. Such representation will be made probabilistic through a small MLP that will produce the mean and covariance of a Gaussian distribution. Each sample from this distribution represents a realization of the underlying stochastic process. We will then get a single sample from the latent distribution and we will use it along with the input features to produce the predictions for the target sequence through the neural processes decoder. Each sample from the latent distribution will produce a new, different set of predictions. We can then compute the global log likelihood with respect to the target labels. In addition, we will compute a KL loss between the representation computed from the random set of points representing the context and from the whole sequence in order to be able to produce, at test time, the contextual representation only from the context points. At test time, we use only the noisy features and predictions for each of the frames in a sequence to compute, for each of them, the mean and standard deviation of its corresponding latent distribution. The per-frame estimate of the covariance represents a contribution to the uncertainty. Using this information, we can select the C frames from the sequence that have the lowest uncertainty and use only these as context from which we can compute the predictive mean of the latent distribution. Using this predictive mean, we can redraw the predictions from the noisy features for the whole sequence. Selecting the context points adds no complexity at all at inference, making our affective processes a very efficient lightweight method. We validate experimentally that our method for context selection works better than using all the frames in the target sequence or by selecting them randomly. In this example, we can see that the predictive mean, in red, better approximates the ground truth, in blue, than the backbone, whose predictions are shown in green. The black dots represent the selected context points using those with the lowest uncertainty. We can see that our method tends to select the most reliable frame to serve as context. We then compare our results against the state-of-the-art for both valence and arousal and action units, setting new state-of-the-art results in 4 databases. You can find more information in our paper. We can see that our method, in red, gives, from the noisy predictions in green, a better temporal approximation to the ground truth, in blue. Our method can effectively model long-term dependencies with very little complexity, being a new promising direction for temporal modeling of emotions. Thanks for your attention. For more information, please see the paper or come to our poster presentation.